Have you ever just stopped and thought about what's right under your feet? And I don't mean just the dirt, I mean way, way down. Well, that's what we're going to do right now. We're going on this incredible journey to the center of the Earth, or, as close as science can possibly take us. So, what's the first thing that pops into your head when you think about it? Is our planet just a giant solid ball of rock? Or is it more like, I don't know, a hollow shell with a really thick crust? It's a huge question, right? And people have been wondering about it for ages. Okay, and here's where it gets kind of crazy. The distance to the center of the Earth, it's almost 6,400 kilometers. Let that sink in for a second. No person has ever made that trip. Ever. No one's ever seen it. So how in the world do we know anything about what's down there? Well, that is where the real fun begins. It's like a giant detective story. Since we can't just, pop down there for a visit, scientists have to hunt for clues. They're trying to piece together this massive planet-sized puzzle. And that brings us to a really important point you've got to understand. Most of what we think we know about the Earth's deep interior, it isn't from seeing it directly. It's all based on estimates and educated guesses, what scientists call inferences. But before we get into all that clever, indirect stuff, let's talk about the few times we've gotten our hands on some direct evidence. So let's start with the most obvious way to find out what's down there, right? We just dig. I mean, humans have been digging holes in the ground forever, and that's how we get our first, most basic, direct clues about what's under the surface. And when we talk about this kind of digging, we're really talking about two main things. You've got your massive gold mines, the commercial stuff, and then you have these special scientific drilling projects, which are all about just finding out what's down there for the sake of pure knowledge. So just how deep can a mine go? Well, if you look at the deepest mines in the world, like the ones in South Africa, they get down to about 3, maybe 4 kilometers, and that is seriously deep. But that's pretty much the limit. And why? One simple reason. It just gets way, way too hot to go any deeper. Okay, so to get deeper than that, we had to get clever. And that brings us to projects like the Kola Super Deep Borehole up in the Arctic. Now, this isn't a mine that people go down into. Think of it as just a really, really deep, skinny hole. But it managed to reach a mind-blowing 12 kilometers straight down. That gave scientists a peek into the Earth's crust like never before. All right, so digging is one way we get clues, but there's another way, and it's pretty cool. Sometimes we don't have to go looking for samples because the Earth sends them right up to us. I'm talking about volcanoes. They're not just spectacular and dangerous. They're actually giving us direct information from deep inside the planet. I mean, think about it. When a volcano erupts, all that molten stuff, magma, gets shot up onto the surface. And once it's out and cools down, well, now scientists have a physical sample they can take back to the lab and study. It's like a delivery service from the Earth's interior. Yeah, that molten rock is what we call magma. And you can almost think of it like a message in a bottle sent up from below. Every time a volcano erupts, it's bringing up a new piece of the puzzle, telling us a little more about what it's like down there, what it's made of, how hot it is. But, and this is a big but, there's a catch. Having a direct sample is amazing, for sure. The problem is it's really, really hard to figure out exactly where it came from. Like, what depth did this specific blob of magma start at? Was it 50 kilometers down? 100? We just don't know for sure. So it's a super valuable clue, but it's also kind of mysterious. Okay, so let's recap for a second. We've got two main ways of getting our hands on direct evidence: what we can dig or drill down to, and what volcanoes spit up at us. Now, let's put it all together and ask the big question. With all that, how far have we really gotten on this journey to the center of the Earth? And this is where the scale of the challenge really hits you. Remember that super deep hole? Our absolute deepest reach into the planet is 12 kilometers, okay? And the total distance to the center? Over 6,000 kilometers. So yeah, what does that tell you? It tells us that with all of our amazing technology, with all our effort, we have barely, and I mean literally just scratched the surface. That's it. It's like trying to figure out everything about a giant apple just by looking at a tiny scratch on the skin. We've only seen the very, very top layer. So that leaves us with a massive question, doesn't it? If all our direct evidence is just from this tiny, tiny scratch on the surface, Then how do we know all that other stuff, about a liquid outer core and a solid inner core? Where did that information come from? Well, that's where the indirect clues come in. Things like tracking earthquake waves as they travel right through the planet or studying our magnetic field. That's how we really start to listen to the secrets of our own world. Have you ever just stopped and wondered what is actually beneath your feet? I don't mean just, some dirt and rock. I mean thousands of kilometers down, right at the very heart of our planet. It is one of the biggest mysteries out there, really, because it's a place we can never, ever visit. But today, we're going to put on our detective hats and figure out exactly how scientists solved this incredible puzzle. So this is the big question, right? How on earth do you map a world you can't see? Well, it turns out it's a fantastic scientific detective story. And like any good mystery, it's all about finding the clues. And just to really wrap your head around the scale of this challenge, take a look at this. The absolute deepest hole humans have ever dug is a gold mine in South Africa. It goes down about 4 kilometers. That sounds super deep, right? But the center of the Earth is more than 6,300 kilometers away. Our deepest reach is, like, barely scratching the paint off of a bowling ball. It's nothing. So, since we obviously can't just go there, scientists have to get clever. They rely on what they call indirect sources. Think of these as the breadcrumbs, the fingerprints, the echoes left behind, all these little things that let us build a picture of a world we can't see. So let's dive in and look at the first clues they started piecing together. Our investigation kicks off with the stuff we can observe pretty directly, right near the surface, from things like mining and drilling. These are the most straightforward, almost obvious clues we have. So it turns out, every time we dig down, we learn 3 really fundamental things. The deeper you go, the hotter it gets. No surprise there. The pressure from all that rock piled on top of you gets immense, and the materials themselves, they get more and more dense. And these aren't random changes, they're predictable patterns. And here's the really crucial part. It's not just that things change, but we can measure the rate of that change. So scientists can calculate exactly how much the temperature and pressure increase for every kilometer you go down. And once you have that rate, you can make a pretty solid estimate of what the conditions must be like thousands of kilometers further down. Okay, so our next clue is a bit of a curveball. It doesn't come from deep inside the Earth at all. Nope, it actually comes from the complete opposite direction, outer space. This right here is such a key insight. You see, the meteors that fall to Earth are basically leftovers from when our solar system was born, about 4.5 billion years ago. So in a way, they're like a cosmic sample of the original building blocks of our own planet. So when we crack open a meteor and analyze it, we're essentially looking at a piece of the same raw material that created Earth. It gives us a physical chunk of that heavy, dense, iron-rich stuff that we'd expect to find way, way down at our planet's core. It's like finding the manufacturer's sample. All right, let's move on to our next set of clues. And these are fascinating because they are completely invisible. We can't see them, we can't touch them, but we can measure them. And they tell us an incredible amount about the world hiding right beneath our feet. Now, this might sound a little weird. I mean, we all learn in school that gravity is this constant force, right? It just pulls us down. But what if I told you that's not 100% true? The pull of gravity actually changes a little bit depending on where you're standing on the planet. One of the big reasons for this is that the Earth isn't a perfect ball. It actually bulges out a little at the equator. This means that if you're standing at the North Pole, you are physically closer to the planet's massive center than someone on the equator is. And because of that, gravity pulls on you just a tiny, tiny bit harder. But wait, it gets even cooler. Because even after you account for the planet's shape, there are still these little variations in gravity. These tiny differences are called gravity anomalies. And what these little wobbles tell us, well, that's the really incredible part. You see, these anomalies are a direct clue about what's hiding underneath. If the gravitational pull in one spot is a bit stronger, that means there's more mass, denser rock, buried below the surface. If the pull is weaker, there's less mass. It's almost like having an X-ray map of the density of the Earth's crust. And hey, it's not just gravity that acts as our invisible guide. Scientists do the exact same thing with magnetism. By conducting magnetic surveys, they can map out where all the magnetic materials, like iron ore, are hidden in the crust. It's just another layer on our growing map of this hidden world. So far, we've looked at heat, pressure, rocks from space, and invisible forces. But now we get to the single most important piece of evidence in this whole investigation, the one clue that truly blew the case wide open and unlocked the secrets of the Earth's interior. This is our star witness. That's it right there. Earthquakes. As terrifying and destructive as they can be on the surface, the waves they send rippling through the entire planet, they are, without a doubt, the most powerful tool we have for seeing what's inside. Seriously, think of it like a planetary-scale ultrasound. An earthquake sends out different kinds of shockwaves, and by listening to those waves with sensors all over the globe, we can figure out what kind of stuff they traveled through. For instance, some waves called S waves can't travel through liquid, and what scientists noticed was that these S waves would just vanish when they hit a certain depth. They created this huge shadow on the other side of the planet where no S waves could be detected. And that was the smoking gun. It was the undeniable proof that the Earth has a liquid outer core. Amazing. So, we've got all these different clues coming from completely different fields of science. The final act in our great detective story is putting it all together to finally see the complete picture. And this just lays it out so perfectly, doesn't it? We started with the obvious stuff, measuring changes in heat and pressure. Then, we looked at samples from space to understand what our planet is made of. We mapped the invisible forces of gravity and magnetism. And finally, we listened to the echoes from earthquakes to draw the lines between the layers. Each clue perfectly confirms and sharpens the others. And that really is the biggest takeaway here. No single piece of evidence could have ever solved this mystery on its own. The real genius is in weaving all these different threads together, from geology, from astronomy, from physics, to build this incredibly detailed and reliable model of a world that we can never, ever visit in person. It really makes you wonder, doesn't it? From the inside of our own planet to the farthest corners of the universe, or even the tiny world inside a single atom. What other giant mysteries are we solving right now? Not by looking at them directly, but by masterfully piecing together the clues they leave behind.
All right, let's dive right in. We're talking about something that's both absolutely terrifying and, honestly, pretty fascinating. Earthquakes. What is one, really?
I mean, think about it. The one thing we count on to be solid, to just be there, is the ground beneath our feet. So, what in the world could make it suddenly start to shake? And sometimes, violently shake, with zero warning.
Well, when you boil it all down, the basic definition is super simple. An earthquake? It's just the shaking of the earth. That's it. It's not something we cause. It's a totally natural event that's been going on since the Earth was the Earth. Okay, but here's the key. This shaking isn't just some random rattling. No, it's all about a massive, sudden release of energy. You know how when you toss a rock into a pond, you get those ripples spreading out? It's just like that. But instead of a little pebble, you've got this incredible burst of energy. And instead of water, those waves are traveling through solid rock. Wild, right?
So, that's the big question, isn't it? If all this shaking is caused by energy, where does that much energy even come from? Where is this powerhouse hiding, and how does it store up all that power?
And the answer, believe it or not, comes down to one word: a fault. Now, it sounds complicated, but it's not. A fault is basically just a big crack, a sharp break in the huge slabs of rock that make up the Earth's crust. And that simple little crack, well, that's where all the action happens.
Okay, so let's walk through this step by step. Picture two gigantic blocks of rock. They're trying to slide past each other, pushing in opposite directions. But here's the problem. They get stuck. Immense friction just locks them in place. But the pushing doesn't stop, right? So the pressure just builds and builds and builds, so much so that the rocks actually start to bend and warp. And then, finally, snap. That pressure becomes too much. It overcomes the friction and the blocks suddenly slide past each other, letting go of all that pent-up energy in one go. Yeah, that is the moment. That abrupt, sudden snap, that's the earthquake. All that energy that was stored up for maybe hundreds of years is just unleashed in a single instant. It's just this incredible release of tension, sending those seismic waves racing outwards.
Okay, so we've got the why and the how. But what about the where? Let's get specific. Scientists have a couple of really important terms to pinpoint exactly where an earthquake starts.
And this is a really important one to get right. Focus versus epicenter. Think of the focus as the real ground zero. It's the actual spot deep underground where the rock finally slipped. It's also called the hypocenter. Now, The epicenter is what we usually hear about on the news. That's the spot on the surface directly above the focus. It's the X on the map.
So why do we care so much about the epicenter? Well, because it's the spot on the surface that's closest to the action. It's the first place those energy waves hit, and that's usually where the shaking is going to be the strongest.
All right, let's do a super quick recap of what we've covered. 1. Earthquakes are just the Earth shaking. 2. It's caused by a sudden blast of energy from rocks slipping along a fault. 3. The real starting point, deep underground, is the focus. And 4. The spot on the surface right above it is the epicenter. See, not so complicated when you break it down.
So we figured out why the Earth shakes. We've even pinpointed its location. But that still leaves one huge question, doesn't it? We know this energy gets released, but how? How does it actually travel all the way through miles and miles of solid rock to get to us on the surface? Now that journey is a whole other story.
You know, we usually think of earthquakes as this destructive force. But what if their real power wasn't just in shaking the ground, but in revealing secrets hidden thousands of kilometers beneath our feet? Today, we're going to use the incredible energy of seismic waves to see deep inside our own planet.
Okay, so let's just jump right into the big mystery. The deepest hole we've ever managed to dig is just over 12 kilometers deep. That sounds like a lot, but the Earth's core, that's almost 3,000 kilometers down. So how in the world do we have any idea what's there? Well, believe it or not, the answer comes from the very thing that shakes our world, earthquakes.
You see, the key to unlocking these secrets isn't some super advanced drill bit. No, it's the powerful vibrations that earthquakes unleash. You have to stop thinking of them as just random tremors and start thinking of them more like waves of energy, creating a planetary-scale ultrasound that travels right through the Earth.
So when an earthquake happens, it sends out these waves in every direction. And all around the globe, we have these super sensitive instruments called seismographs just listening for them. By looking at how these waves travel, where they show up, and, this is the important part, where they don't, we can actually start to build a picture of what the Earth's interior looks like.
Now, not all earthquake waves are created equal. An earthquake actually generates a few different kinds, and figuring out what they are is the first step to decoding the messages they carry. The two main families are body waves and surface waves. Surface waves, just like the name says, travel along the crust. They're the ones that cause all the shaking and the damage we associate with quakes. But for our investigation, we care about the body waves. These are the deep divers, the ones that travel right through the body of the planet, carrying clues from way, way down below. Okay, so let's zoom in on those body waves. Inside that family, you've got two key players that act as our primary scientific detectives. We call them P waves and S waves. P waves, or primary waves, are kind of like sound waves. They push and pull the rock they move through. They're super fast, so they're the first to show up at a seismograph station. Then you have S waves, or secondary waves. They're slower, and they move material up and down. But here's the single most important difference. P waves can power through pretty much anything, solid, liquid, or gas. S waves, though, they have a fatal flaw. They absolutely cannot travel through liquid. They can only move through solids. Now remember that. It's the key to this whole thing. Because that one simple fact about S waves, it leads us directly to a massive planetary mystery. A weird phenomenon that scientists started noticing over 100 years ago called the shadow zone. So you'd think, right? A big earthquake happens, and its waves should travel outwards and be picked up by seismographs pretty much everywhere across the globe. I mean, they radiate out from the source in all directions. But that is not what happens. Not at all. Scientists noticed that in certain very specific areas on the other side of the planet from an earthquake, their instruments picked up, well, nothing. Just a strange, predictable, eerie silence. And this area of silence, it's called the shadow zone. It's a region where the Earth itself seems to be blocking the earthquake's waves. But the mystery gets even stranger when you look at which waves are being blocked and where. So those P waves, or go-anywhere waves, they do have a little shadow zone. It's this thin ring around the planet. And that's because the waves get bent or refracted when they pass through different layers of the Earth, which leaves a small gap in coverage, but it's nothing huge. But the S-wave shadow zone, that's the real smoking gun here. It is not a narrow band. It's a gigantic chunk of the planet. Any seismograph that's located more than about 105 degrees away from where the earthquake started detects absolutely zero S-waves. They just vanish. And to put that into perspective, the S-wave shadow zone covers a little over 40% of the Earth's entire surface. It's a massive planetary-scale dead zone just for these specific waves.
So this leads us to the big, obvious question, right? Why? What could possibly be inside our planet that's big enough to just stop all S waves from getting to almost half the globe, while at the same time letting most of the P waves pass right through?
And there it is. The answer is so elegant. The only possible explanation is that there is a massive liquid layer deep inside the Earth. The S waves cruise along through the solid mantle just fine, but when they hit this gigantic liquid barrier, they're stopped dead in their tracks. This is the evidence, not from a drill, but from shadows, that proves our planet has a giant, molten liquid outer core. It's just incredible.
I mean, proving there's a liquid ocean of metal under our feet is amazing, but it's not the only thing seismic waves can teach us. By studying these events, we also get a much clearer picture of what causes them in the first place and how we actually measure their power.
So while most quakes are tectonic, caused by those giant plates shifting around, they can also be kicked off by anything from volcanic eruptions and collapses in mines to even man-made explosions. And when we talk about measuring them, it's really important to know the difference between these two scales. The Richter scale tells you the magnitude. That's the raw energy the earthquake released right at the source. But the Mercalli scale measures intensity. That's the actual shaking and damage you would see or feel on the surface. So a single earthquake has only one magnitude, but it can have a bunch of different intensity levels depending on where you are.
So just think about it. By listening to the silence just as much as we listen to the noise, seismic waves gave us a window into the very heart of our planet. It really makes you wonder, what other planetary secrets are still waiting down there, with these echoes just trying to tell us about the world beneath our feet, if only we can figure out how to listen?